In this video, I'll be showing how to properly solve a conservation of momentum problem. First of all, momentum refers to the quantity of motion that an object has and is also a vector quantity denoted by P that is a product of the mass and velocity of an object or particle. Conservation of momentum is especially relevant when it comes to collisions, specifically and only elastic collisions in which two objects, let's say object A and object B, collide, then bounce off each other, resulting in no net loss of kinetic energy and no net loss of momentum. Now, first things first, regarding the formula for the conservation of momentum. Now, since momentum is the product of mass times velocity, the initial momentum formula for object A will be mass of A initial times velocity of A initial. And since it's conservation, we'll go ahead and equate it to mass of A final times velocity of A final. And since it's two objects, we also have to do the same for object B. So mass of object B initial times velocity of B initial equals plus mass of B final times velocity of B final. Now let's take a look at this problem. This problem, we have two cars, car A and car B, that collide and bounce off each other. Now the problem asks, what is the final velocity? Now in this problem, we see that car A drives in the southeast direction down at 30 angles with a velocity of 20 meters per second, while the car B drives in the northeast direction at an angle at 20 degrees at 30 meters per second. Now we are given that car A, after bouncing off of car B, bounces off and drives off at 40 meters per second at an angle of 35 degrees in the northeast direction. However, we do not know the angle nor the final velocity nor magnitude of car B. Now, in order to solve this problem, and since we are given angle directions, we do remember that momentum is a vector quantity, meaning that the momentum and velocity, or the velocity, can be separated into vector quantities I, or the x component, and j, which is the y component. Therefore, we can just separate all of these quantities like so. So just to remind everyone, I, j, the x component, and the y component. And so we have the original equation, MAI times VAI plus MBI times VBI equals AF times VAF plus MBF times VBF. Now remember that the problem said that both masses of the two cars are equal. Therefore, we can go ahead and just cancel out all the masses in order to find the final velocity of car B. Now, since we can separate these by components, we can go ahead and first do car A. So by trigonometric rules, for the x component, it would be adjacent hypotenuse, so cosine. So for the A, it'll be 20 cosine 30 degrees. That would be the I component for car A. And then for J, it would be sine opposite hypotenuse, so it'll be 20 sine 30. Now, since this car is going in the southern direction, this J or Y component is going to be negative. And then now we have to do the same for the car B, the component for the velocity. So this is 20 degrees and this is going in 30 meters per second. So we have, for the J component, it is gonna be opposite over hypotenuse, so it'll be 30 sine of 20. And then adjacent hypotenuse, it'll be 30 cosine of 20. And then for this, for the final velocity, the components for that, same thing. So this is 35 degrees and this is 40 meters per second. So for the I component, it'll be adjacent hypotenuse, so it'll be cosine, so it'll be 40 cosine 35. Let me just... And then this opposite hypotenuse, that'll be 40 sine of 35. And then you just solve for all of these, and that will give you the I and J components for VB for the final velocity of car B. So I've already computed all the vector components for each velocity. So these are the I and J's for VAI, for the initial velocity for car A. These are the I and J components for the initial velocity of car B. This is the I and J components for the final velocity of car A. And then all you have to do is solve algebraically in order to get the I and J components for car B. So if you just add the initial velocities of car A and car B, subtracted from the final velocity of car A, that would give you, for the I component, that would give you negative 12.75. And then for the J component, all you have to do is do the same thing. So subtract the J components for the initial velocities of car A and car B, subtracted from the J component for the final velocity of car A, and that'll give you 22.68. Now, since vectors have I and J components, or X and Y, in order to find the resultant vector between the resultant component from I's and J's, you would just have to follow the Pythagorean theorem, i.e. a squared plus b squared equals c squared, or in this case, I squared plus j squared equals the resultant velocity. Therefore, you would just have to do the same to find the magnitude of the final velocity of car B. So, since this is I and J, you would have to do, or squared, so it would be negative 12.75 squared plus 22.68 squared, root. And that would equal second squared, negative 12.75 squared, 22.68 squared, 18.757 meters per second. And this is the magnitude of your final velocity for car B.